Okay, so today we're talking about two-way tables. And the main point of a two-way table is to organize your data from a survey. And because the data is collected in categories instead of like numbers. And so what you want to do is it's for categories. And it can help organize your information. In the past, you've probably seen something like this diagram here, which is called a Venn diagram, where the categories, if you have two categories, you would have, say, category A, and then you would have category B on questions, and then inside in the middle here, the combination of both of them would be A and B. And then, of course, outside, if it's not part of A and not part of B, then it would be neither A or B. And that's how data probably was organized, and you've seen that before. But, so here's one. This is a Venn diagram. And a survey was done for the school newspaper in which they surveyed a total of 175 students. So we've got 175 students total. And out of those students, 28 had a new phone. And 44 had a laptop. So two questions. Do you have a phone? Do you have a laptop? And these are the results. And if you don't have a phone or a laptop, you got neither, and that was 110 students. So, the question we've got to answer is how many students have the new phone or the laptop? Which means, in essence, you've got that phone or you have a laptop, but it's not both. And so if we start organizing the data with the Venn diagram, we've got our nothing outside. So we've got 110 students here. And if we want to look at some percentages with that, that would be 110 divided by the total of 175, which gives us 63%. So 63% didn't have anything, and the rest had something. So if we look at this a little closer, we know that, let's find out that how many of these, let's focus on our question here, how many had both. So we know that 175 is a total. We know that 110 had nothing. We take that difference and we get 65 students have something. Either a laptop or a phone. And if we look at what we are given, we know that we have 28 students, which are going to be somewhere in category A. Here. Okay, let's make that a little thicker. Category A here. And then we have category B here, which is the 44. So somewhere in here are the laptops, and then somewhere in here are the phones. But the one thing that we don't know is how many are going to be in both. So how many have both? Because it doesn't tell us that. So that's the one thing we've got to figure out. So if we take this 65 and we take our 28 and our laptops and we put them together, put our phones with our laptops, we would get 28 plus 44. And that gives us a grand total of 72, which is not the same as our 65. So if we take the 72, take away the 65, that gives us a difference of 7. And that's how many would have both. So we now know that 7 have both. And that's 7 out of 175. Which is going to be equal to 4%. And then if we take our 28 minus that 7, and we take away the 7 of both, that gives us 21. So we now know that 21 are the ones that only have a phone. And if we do the same thing with our laptops, 44 minus that 7, we end up with 37. So we now know that 37 have only a laptop. And if you add up 21, 7, 37, and 110, you get your 175 total. Because 21 and 4 is 28, 28 and 37 is 65. So, let's look at some percentages here, because we have enough information to answer our question. It's 21 plus 37. And so this is the phone only, and this is the laptop only. And so that comes down to a total that have a phone or a laptop. So this is our or, and it's the answer to the question, which is 58. And the percentage of 58 is 33%. So that answers our question. But if you know me, it's not enough. So let's find the percentages here. So that's 21 out of 175 have only a phone, and that's 12%. And the 37 kids out of the total 175, that's 21%. So now we've got a completed Venn. And yes, it's a lot of work, but now the data is now organized. Comparing that to a two-way table, so a two-way table, we take our information, and this is how the information is. So we've got our laptop kids here, and there's our 44. If We've got our iPhone kids go across this row, or iPhone kids, whatever. Our phone kids, there's our 28. Here's our 110 that didn't have anything. And then here's our 175, which is a total, which is 100% of everybody. So we need to start filling in some data, and you start looking for holes, and you need two, because then you can find a third just with subtraction. So the first place that I'm going to look is under no phone. If you take the no phone all the way over, and we got our numbers here. Well, 28 from 175 is 147. And so the 28 divided by, the percentage of the 28 is 16%. So this number here, this is 16%, 28 divided by 175. And we take the 28 from the 175, we get our 147. And 147 is 84%. And that's simply 16% drawn and subtracted from the 100. So if that 147 with this 147 is our total for no phone, just the kids that don't have a phone. 147, and then we can look at no phone and laptop. 110 from 147 is 37. And that's 37 over 175. And that percentage is 21%. This 44 divided by 175 is 25%. And if you take 25% from 44%, you end up with 4%. Or 21% from 25%, you get 4%. So that 4% ends up being 0.04. Well, we also know that it's also going to be 7 kids, because 37 from 144. And then 7, we can now look at the phone category. That if we have 7 kids here and 28 kids, then this has to be 21 students that have a phone and no laptop. So that gives us 12%, because 4 plus 12% is 16%. And the 110 kids that don't have anything, we already know that that's 63%. But that's simply 110 divided by 175. And 21 plus 110 is 131. And so that's going to come down to 75% approximately, because 25% plus 75% is 175%. So now we want to calculate what is the probability. So the question we want to look at are these two questions here. The first one is question number 1, question number 2. Question number 1 is, what is the probability a student at his high school has a phone or a laptop? So if we look at this table compared to this Venn diagram work, it's a little more organized, a little more tightly seen, and the numbers tend to fall into certain categories more easily. So we've got our laptop in blue. We have no laptop with double arrow down. We got the brown arrow to the right of no phone. And we have our red category of the iPhone. So here's our original 2 that we had. So if they have a phone or a laptop, which means the probability that they have a phone or a laptop. Let's organize this a little better. The probability P that a person has a phone or a laptop. And that's going to simply be, you just look for the numbers for that. And the phone only, this means only a phone or a laptop, not both. So the probability of having a phone or a laptop, you just go in and grab the phone only percentage, which is 12%, plus the laptop only no phone, which is 21%, and then you get 33%. And what is the probability that a student has a phone and a laptop? And you can see that we know that the probability that a student has a phone and a laptop is the one where the phone and laptop share a box. And that's this one. Here. And that is our phone and laptop. So you just take those two percentages. Well, actually it's 1%. It's 4%. Or 7 out of 175, which is 4%. So the table is a little more tight. The numbers tend to follow some a little bit better order, so it's a little bit more organized. By what we're looking at is categorical data. So it's more organized by the categories. So another question we have here is looking at mutual exclusivity, which can talk about associations within categories. Inside, which takes us in the idea of subcategories, but I'm just going to say within or inside the categories. So, is there an association between owning a laptop and owning a phone? Meaning, if you own a laptop, are you more likely to own a phone? So this is our question we're looking at right here. And the way we're going to do that is, first we're going to calculate the probability of a laptop owner owning a phone. So the probability of a laptop that also owns a phone, which is the exact same thing as the probability of a laptop and a phone, which we already know is going to be, if we look back at our data, that's 7. So we're looking at laptops and phones, and the students that have a laptop. So all the students that own a laptop is 44. So we got our blue 44, which is our total. And then if we look, there's 7. So of the kids that own a laptop, the total of laptop owners was 44. And we know that there was 7 kids that had both. So 7 out of the 44 laptop owners also had a phone. So our percentage is 16%. And we're going to compare that to the probability of a non-laptop owner. So first off, we have the probability that laptop owner owns a phone. So first we looked at, so that's where we looked at the laptop owners, of which there was 44. So now we're going to look at non-laptop owners owning a phone. The probability of no laptop and having that phone. So the total kids that owned a phone, just a phone. If we look at our table, you look at the red, which is just a phone, and no laptop, which ends up being 21. So we have a grand total of the people that own a phone only was 21. And the total number of kids in that category of no laptop is here. No laptop. And the total for that is 131. So the probability is simply that 21 divided by that 131. And that ends up equaling 16%. So if you compare the percents with question 1 and question 2, our answer to question 1 was 16%. Our answer, so the probability of 1 was 16%. The probability of question 2 ends up being 16%. So the answer to our question is no, because both are 16%. And so they have the same chance of having a laptop and a phone as no laptop and a phone. And that is all by the categories. And that's the categories of students in the category. So, our next question here is using a two-way table to solve this problem. If there are 145 students enrolled in a senior level fitness class at a high school, 116 boys and 29 girls. So there's 145 students, 116 are boys and 29 are girls. So we got 145 total. We have 116 boys and we have 29 girls. And out of that, 24 of the boys and 7 of the girls earned an A. So we can take that right now. 24 of the boys earned an A. So here's our boys, which means the total is 116. And so that gives us 92 boys did not get an A, because 24 and 92 is 116. And then we look at the girls, and we have 7 of those girls earned an A. And there's 29 total. And that gives us a total of 22 did not earn an A. And if we look at these, check our numbers, 116 and 29 is 145, which is our 100%. So if we look at the number of boys that earned an A, that 24 ends up being, by some simple division, 21%. And this next one has to be 79%, because 92 divided by 116. And that ends up, and that gives us our 116. Now, the 116 divided by the 145, so this 116 here ends up being a grand total of 80% of the kids. This 21 is of the boys. This 79% is of the boys also. So that's all the boys. But the boys are making up 80%. The girls, on the other hand, that got an A, ends up being 24%. And this 22 ends up with the rest of them, which is 76% of all the girls. And this 29 represents 20% of the 145. Looking a little deeper, 24 plus 7 is 31 total, which is 21% of the kids earned an A. Total 21%, because 24 plus 7 is 31. 31 divided by 145 is 21%. We now have 92 plus 22. That gives us 114 total kids, and that ends up being 79% of the total, and 21% plus 79% is 100%. So the question we've got to answer is here. Is there an association between gender and the grade received? In other words, they're asking, is it more likely for a boy to receive an A than a girl? And so we can solve that simply by looking at the probability of the boy getting an A and the probability of the girl getting an A. Boy and an A versus, sorry about that, versus the probability of the girl and an A. And if we look at our table, we know that the boys and an A was 24 out of 116, which was 21%. And the girls getting an A was 7 out of the total girls, which is 29, which is equal to 24%. So if you compare those two, the girls and an A is a larger percentage. So the answer to this question specifically is no. It is not more likely for a boy to receive an A than a girl. It actually is more likely that a girl earns an A, if you're going by the categories. Now we go on to our next question, which is solving another problem, which is a lot of words, but ultimately it comes down to susceptibility to the DAP or the DAPT genetic defect in blood types. And you might have run across this in your bio class. The researcher collected the following data. We need to make a relative table to determine if there is an association between the blood type and the presence of the DAPT. So that's our question. Is there an association between blood type and the DAPT? And so we're going to compare the probabilities within the blood type categories of having it versus not having it. And if there is a difference, then there is an association. It can be yes, it can be more likely towards no, depending upon the blood type. But we're looking inside the categories of each blood type. So first we're going to look at having the DAPT. So we're going to convert this table into percents. So this is all we're looking at. So if we take, so all of these are people in millions. And it's a little, you got to remember that. Because that's going to end up becoming a percent of people. So the first thing we got to have is, what is our total number of people that have the DAPT? And in millions, we have 0.3 million plus 0.28 million plus 0.07 million plus 0.03 million. So we're looking here. And all of these are millions of people. So we take that and we end up with 0.68 million. And if we take 0.30 divided by 0.68, we get our type O. So this ends up being 44%. And then 0.28 divided by 0.68. So we're taking all of these check marks here and dividing it by the whole. So type A percentage becomes 41%. Type B becomes 10%. And with a little bit of rounding, the rest of those is AB, and that gives us 100% of our 68 million. And so how you get that? You take your category and you simply divide it by the total of that category, which is otherwise known as the whole. Now we're going to look at the percent that do not have it, which is no DAPT, which is this row. And our total here is 311 million, which is a lot larger than less than 1 million. So we go and take our division of 137 divided by 311. We get 44%. And then our next category for type A is 42%, followed by 10%, and followed by 4%, which is the rest. And that gives us 100% of those people that don't have the DAPT. Category divided by total. So if you look at the comparison within the categories, we have 44% versus 44%. So those are the same. And then we have 41% versus 42%, which is pretty much the same. Then we have 10% versus 10%, which is the same. Then we have 5% versus 4%. So this is our red category summary. And we have our blue category summary. So this is the has here. And here we have the not in this box. So if you look at it, the answer to our ultimate question is no. There is no association of blood type and the DAPT. And that's simply because by the categories, they are the same likelihood. So it's the same chance or probability by the categories. And that's what tables allow us to do, is to organize it. Our next question is a problem with the U.S. Census, which is coming up. So there's 312.59 million people living in the U.S. in 2011. The number of people living alone is given in the two-way table, and it's in millions of people. So we have if you look at it, for example, under 25, if we just look at the under 25, just for a quick second, under 25, which is here, we have 145 million people under the age of 25 living alone, and there's 109.67 million people under the age of 25 living with others. So that's how this is done, and it's arranged according to other ages, 25 to 34, 35 to 44. These are our age brackets. So our main question, first one that we have, is what is the probability of living alone? So the probability of just living alone. So only living alone is given by the top row. So what we need to first find is a total for that. So if you add up 1.45, 4.16, 3.55, 5.57, and so on, you just add up the top row, that's going to give us a total of 32.73 million people. Better place to put that. So living alone is 32.73 million people. And we could calculate the number living with others, but it's unnecessary for this problem. Let's save some time. So we know that our total is, total number of people's here. That's our total. So if you add up all the numbers, you get that number, which is 312.59 million people. And if you divide the number of people living alone, which is 32.73, you get 11%. So the probability of living alone is 11%. Now, our next question is, what is the probability of being 65 or over? So the probability that you age is greater than 65. If you just happen to be some random person in the United States. And if you look at the people that are 65 and older, 65 and older are all of these folks, 65 to 75 and over. And so you're looking at the totals of people inside those categories. So if you add up all those numbers, you get a grand total for these two of 39.16 million people. And if you divide that number, 39.16, divided by the entire table, which is the total, which is 312.59, you get an answer which is 13% approximately. 13%. So 13% of the entire table is over the age of 65. And what is the probability of being under 65? Probability your age is less than 65? Well, that's even easier, because that's if you take all the people, which is 100%, and you subtract the 13% that we just calculated, which is over 65, which means the rest of them have to be under the age of 65. And that's equal to 87%. So now we have that number, because if you subtract something you got from everybody, you get everyone else. Now, the probability of 35 years of age and living alone. So you need to be under the age of 35 and living alone is our next question. So the probability that your age is under 35 and you live alone. So that's going to take us to another spot in the table. So first we need to find out where all the people that are under 35. Well, here's 35. So everybody in that direction to the left of that 35 is under 35. So what we do is we have to find out whether they're living alone or not. So if we go to the living alone box underneath that, we get these two numbers here. So there's 1.45 million people and 4.16 million people that are living alone and under the age of 25. And those two totals numbers total 5.67 million people. So we have 5.67 million people that are alone and under the age of 35. And if you divide that by the total number of people, which again is 312.59, the probability of you being under 35 and living alone, pick a random person out of the United States, that's 87%. No, that's not 87%. It's much smaller than that. Sorry about that. 5.67 divided by 312.59, that's 2%. So there's a 2% chance that you're under the age of 35 and living alone if you happen to pull a random person out of the United States. Big hand, reach down, pull somebody up. So to find the probability of being under 35 and living alone, this one dude, Key, added the total number of people in the first two columns to the total number of people in the first row. So he added these first two columns here to all the people in the first row. And so the question is, well, that's not what we did, because we can see in the table it's organized pretty well that we're just looking at living alone and under 35. So what did he do wrong? He didn't take the people under 35. He didn't go under and alone boxes. He didn't take the people that were alone, which was our red, and people with an age of less than 35, which we circled in red as well. Actually, that was brown. Going from age 35 and backwards. And he didn't divide it by total people. He took it specifically total with under and alone. So he took all those that were living alone out of just those that were under 35. So he did not do this. That's what he didn't do. So he looked at the so he just looked at the people that were completely under the age of 35 and then added, so he took everyone that was under 35 and everyone that was living alone. And we only wanted those that were alone and under the age of 35. So he did an OR. He did the probability of or, not the probability of and. So you got to be careful when you read your question. Now, if you're still with me at this point, these are a lot of questions. There's 8 problems. Each problem takes roughly 5 to 6 minutes to explain. And if you're still here, you're killing it. So, the last question. Oh, yes. Last question. The last question is there association between age and living alone? Which basically means, is there a relationship that either the younger you are or the older you are you more likely to live alone, depending upon your age? So that's our question. So we're going to look at the age compared to and living alone as categories. So, there's a lot of number crunching involved in this, but ultimately we are only looking at those that are living alone, which we have all these numbers. But then we're going to take it one step further and go by categories. So we're going to look at each group living alone by categories. So we need to get our totals, our category totals. And let's pick a better color for that. We'll do those in brown. So our category totals, if we take the total people that are under 25, so if we take the total people that are under 25, we get 111.17. And for 25 to 34, the total number of people is 41.57. 35 to 44 is 39.83. Excuse me. And 45 to 54, the total number of people is 43.94. I really hope I'm adding these right. 55 to 64 is 36.77. No, it's 36.97. The total number of people 65 to 74 is 21.4. And the total of 75 or over people by category is 17.76. So that's our category totals. Now, if we just take our alone, those that are living alone, and we divide it by the category totals, which I will call the CAT totals, we will get our percentage of those that are living alone within each age category. So that's going to be here. So we end up with 1.45 divided by 111.17. So we go 1.45 divided by 111.17. And that gives us 1%. So we get 1% for that category. This next one is 10% with a little bit of rounding. Then we have 9%, 3.55 divided by 39.83. Our next category is 13%. Then we have 18%. And then we have 4.81 divided by 21.4, which gives us 22%. And then we have our total for 75 or over is 6.50 divided by 17.76, which is equal to 37%. So we take 6.50 and divide it by 17.76. And that's how we get those numbers. So what we're looking at are these. The percents that are alone divided by the category total. And as you can see, it goes from 1% on up to 37%, and it's pretty much increasing over time. So you could say the answer to our question is yes, there is an association between age and living alone. It actually makes sense because younger kids are less likely to live alone than older folks. So it seems, so we would say yes. The older you get, the chance or probability of living alone tends to increase if you're going by the categories. Now, that had a lot of data in it, but the table is very organized. I challenge you to do this with a Venn diagram so that each one of the categories is a circle. So, that concludes all those problems. Please don't forget the review and preview problems at the end of the section. They show up on quizzes and practice problem sets. So chances are you will see those questions on your practice problem sets. Please remember that my office hours are anytime between 8 a.m. and 3 p.m. And you can reach me on Remind. Good luck. Stay healthy.